it is. You ever sit down, write a chunk of code that you've run buffer smooth, but instead it lags harder than a potato PC running Cyberpunk? Yeah, you've all been there. In today's video, we are diving into why that happens, and it's not always your logic that's the problem. Sometimes it's where your data lives. Let's talk performance, caching, and how your code might be leaving CPU horsepower on the table. Let's go. So here's the thing. Your CPU doesn't just grab data from your hard drive or even your RAM every time it needs it. No, that will be way too slow for how fast your CPU thinks. Instead, it uses this lightning-fast space called the CPU cache, a tiny but mighty memory space that lives inside the CPU itself. So imagine you're cooking. The CPU cache is like your kitchen counter, super fast and it's right there. The RAM is more like the fridge, still in the house but it takes a bit longer to grab stuff. And storage is like a grocery store. You got to get in the car and drive there. Every time your code forces the CPU to go grocery shopping for data, its base cycles, introduces latency, and slows everything down. A cache tries to be smart. It predicts what your CPU will need next and preloads the data in chunks, not just one memory address, but the addresses around it too. So if you access data that's next to each other in memory, like walking to an array linearly, you are more likely to get a cache hit, meaning the CPU already has the data handy. But if you jump out on memory randomly, that's a cache miss, and it has to go all the way back to RAM or even storage. Yikes. Let's say you're walking through an array, and you see this. The first thing that comes up to your mind is, why? Because sequential access keeps the CPU cache full. It loves the surrounding values too, so the next value is already there when needed. Random access, it's like opening 20 tabs and all tapping between them. Your brain or the CPU gets confused. Arrays store data contiguously in memory. Linked lists, they're all over the place. Each node is a pointer to the names scattered across memory. That means arrays are cache-friendly highways, while linked lists are being memory scavenger hunts. Use arrays when you can, especially for performance-critical tasks. The last thing I have to say is always provide your coding. Just don't guess, measure. Use tools like Unity Profiler for Unity devs, bar grind, cache grind, Brief if you're a Linux user, IntelliVidTune, and Chrome Web Tools for web developers. Profiling shows exactly where your code is slow, and whether it's due to cache misses, CPU stalls, or just bad logic. You'll be surprised how many fast-working functions turn out to be silent killers. So that's a crash course on how caching works and how you can write code that plays nicely with your CPU. If you learned something new, smash that like button, and if you're not subscribed yet, what you been doing? Hit that sub button. It'll help Java more than you know. Let me know in the comment section if you want a part 2 and where we dig into stuff like multi-threading, foreshadowing, and how different cache levels work. Until next time, keep coding smart and I'll catch you in the next one.